Welcome, class. We left off running hypothesis tests for two populations where we were testing the difference against a zero. That is the most common. Every once in a while, we'll have a problem where we're testing against a number that is not zero. Here's an example of that. I'll let you read that a moment. In this particular problem, we're not testing against zero. We're basically saying we believe the innovative new method is better, but it's also more expensive. So we are determined that we want it to be at least 5 points better for us to be willing to pay the extra money. That's what we're testing against. Is it 5 points better? Not just better, comparing the difference to zero, but comparing it to the 5. So that's an example where we're not testing against zero. We're looking, does this company have strong evidence they should use the new method? Okay, well, let's first of all define what our populations are, okay? The first group, the first sample given was the first method, which is the traditional method. So we begin by saying that our mu1 equal the mean of the traditional method. We let our second mean population be the mean, in this case, of the new method. So now I go back and I try to find my null and my alternative. Both of them, like we've done in the past, are a difference. So it's mu1 minus mu2, mu1 minus mu2. Let's make sure now we get this one straight, the alternative. That's the one we have to be careful with, okay? We're looking to see if it's 5 points better, the new method. The second number, mu sub 2, must be at least 5 points bigger, higher. If this is the bigger number, smaller minus the bigger, it's going to be a negative number. So it's got to be less than, it's got to be a negative number on the negative side, but it's got to be less than a negative 5. Because if this larger number subtracted from the smaller is going to be 5 points better, that difference has to be less than a negative 5. This one, it can either be greater than, or I could have just put down equal to a negative 5. Greater than or equal to, either one would have been okay. This is the one that's crucial. Again, you don't need this drawing over here, but I'm going to put it out there just to help us understand where we're coming from. We're testing against the negative 5. So you're putting a negative 5 right here. The z-score would have been 0 for that, okay? They want us to run a p-value test. So we'll come back to that in a moment. The p-value test is going to have my p-value on just the left side. Okay? I'll get that p-value eventually from my, in this case, z-score. They're asking whether I have strong evidence. Strong evidence indicates that alpha is 0.05. I had a sample of 80 in this one, and we put, 40 in each group. So each sample size was 40. Because of that, both are bigger than 30. I can use a z-stat. I am looking for a p-value test, so I do not need a rejection region. I'm going to calculate my z. This again is that little more complicated formula. It is x1 bar, that's the mean from the first sample, minus the mean from the second sample, minus our hypothesized difference. This time that's a -5, all divided by the square root of my first standard deviation squared over the sample size plus the second standard deviation squared over that sample size. Pretty complicated looking formula. The first sample mean, in this case, let's go ahead and find it once. The sample mean of the original method was 84.9, so x1 bar is 84.9. The other one is 91.3 minus our hypothesized difference, which is a -5. So I'm really going to have minus a -5 there. All divided by square root of 2.8 squared over 40 plus the 3.1 squared over 40. You need to run that through your calculator. It does take some work, but here's what you end up getting. You end up getting for a z-score a -2.12. So again, make sure that you can get that number from your calculator. I need to find the p-value. This is a single-tailed test, so it's going to be a 1 times 0.5 minus the p-value, or the probability value of 2.12. Turns out that is off of your normal chart, that's going to be a 0.4830. That's going to give you a p-value of 0.017. That p-value, 0.017, technically is in there. We compare that to our alpha. If this p-value is less than alpha, which it is, then I have sufficient evidence to reject the null and conclude that it is 5 points higher. If this p-value had been greater than 0.05, then I would have had insufficient evidence to reject the null, and I would have had to continue to assume that it's not 5 points greater. This one, though, is enough evidence. So I state here in step number 4, I state p equal to 0.017 is sufficient. I'm going to slide this up so you can read it as I go. Sufficient evidence to reject the null, and now conclude the new method. I'm trying to put it in context now. The new method of training is at least 5 points higher. that would be the mean is 5 points higher, okay? Again, I just want to emphasize, when you have sufficient evidence, you now conclude the alternative. Okay, sufficient evidence, now conclude. The 95% interval, to calculate that, our formula for a 95% confidence interval is going to be x1 bar minus x2 bar plus or minus our z-score times our adjusted standard deviation, which is that denominator here. So it's this formula right here. It is the square root s sub 1 squared over n1 plus s sub 2 squared over n2. Calculate all of that. We'll be putting those numbers in here. So now our 95% confidence interval, it's going to be these same means that I had right here, 84.9 minus 91.3. The Z for 95% confidence interval is 1.96. Putting these same substitutions in that I did right here. So it's 2.8 squared over 40 plus 3.1 squared over 40. When you end up getting that all calculated out, this first of all would be a negative 6.4 plus or minus 1.295. Make sure that you can get from your calculator to this 1.295, and you need to add and subtract it. And when you do, this is what your interval turns out to be, a negative 7.695 to a negative 5.100. This interval is just a little bit more difficult to interpret. First of all, we could say that it's all negative, but that might only indicate that the second method is a little bit better than the first. We want it to be at least 5 points higher. That means that this interval has to be less than a negative 5, because we were comparing it to the negative 5. Notice the entire interval is below the negative 5. That indicates that we are 95% sure that the second method is at least 5 points higher. Basically the same conclusion that we had with the hypothesis test. This is what you would all need to write down for your hypothesis test. This is what you would have written down for your confidence interval. Both of these had sample sizes of 40. They were large samples, okay? Next, we're going to talk about what happens if we have small samples. What happens if we have small samples? I mentioned earlier that our formulas got messier when we had to compare two populations. This is the previous one. What I meant by that is this formula right here got messier, the Z formula. The confidence interval got messier right there. That gets even more so when we have small samples. Small samples would be if either sample is less than 30. Don't panic, you don't have to write this down, but just look at it once. If either sample is less than 30, it would be a small sample, which means we'd have to run t-scores. Most of the time, the standard deviations are unequal. Once in a while, they are approximately equal. If they are approximately equal, we have a little bit more power in detecting a difference. We say the test is more robust. It has more power in detecting the difference because we're able to get much more sensitive to that difference by this adjusted standard deviation. Don't panic, don't write that down. You're not going to have to use that. If they're not equal, we have to go back to this formula, which looks like it's, and it is, exactly the same as the z. However, our degrees of freedom is a very complicated looking formula. Up here, when they were approximately equal, the degrees of freedom was n1 plus n2 minus 2. Well, where did that come from, actually? Do you remember previously our degrees of freedom was always n minus 1? Well, now if I have two samples, it would be the first sample minus 1 plus the second sample minus 1. When you combine those, that's where they get this, n1 plus n2 minus 2. So that's where that expression comes from. This one, unfortunately, is much more challenging. Because these formulas get to be so messy, for any problems in this chapter where we are forced to use small samples, I will either give you the t and the degrees of freedom, or more often, most of the time, you're going to get these in a computer printout. You're not going to have to calculate these. I'm going to say that again. When we are given small samples, we will be given these in a computer printout. When you're given large samples, then I would expect, this is again the previous sheet, then I would expect that you can grind it out in your formula, but not for these small samples. Again, do not copy this down, but this is for a confidence interval, small sample. Approximately equal variances. Doesn't look too bad, except notice this right here. That's this entire formula has got to go right in there. Again, very, very messy. Degrees of freedom, not so bad, but this again is a very messy adjusted standard deviation. That same adjustment would have shown up right here for the t-score for your hypothesis test. Again, very messy. Let's now run through a problem that has small samples. I'll give you a chance to read that a moment. Make sure we understand what we're testing in this problem. We're basically testing, does the Ford Edge get better mileage than the Ford Explorer? We're looking to see if I have strong evidence of that, if I have mathematical evidence that the Edge gets better mileage. The Explorer got 17, the Edge got 18.5. Well, 18.5 is above 17, but is it far enough above that we say we got mathematical evidence? Do we have evidence that is statistically significant? That's what this test is about. Again, I'll need to define each of my populations. I take whichever one was given. Because the Explorer is given first, that's the one I use for my first population. So this is going to be the mean miles per gallon. I'm just going to go with MPG mean miles per gallon for the Explorer. And the second one was for the Edge. So it's the mean miles per gallon for the Edge. Then I'm ready to go to my null and alternative. The null on the left, the alternative here. Let's determine now, first of all, both of them will be describing a difference. Let's see if it's two or tailed or single tailed. Notice I'm looking to see if there's evidence to indicate that the Edge gets better mileage. Better is not like, is it the same? But we're asking, is the Edge better? That's a single tailed test. The Edge is the second one. I'm looking to see if the second one is a bigger number, a bigger number. If I take a bigger number, subtract it from the smaller, that would be a negative difference. That's why I'm looking to see if it's less than 0. This one would be equal to 0. I could have put greater than or equal to. I'm just going to go with that one. This one has to be less than. This is the most important. Again, what am I actually looking at? I'm testing, is the difference 0? Or is it going to be so far to the left, the negative sign? Is it going to be way over here, which means I'll have statistically significant evidence to indicate the Edge is better? Or is it going to be over in here someplace, where we would say it's still reasonable variance? Well, let's grind through our work. They asked if I had strong evidence. That's an alpha at 0.05. My two sample sizes, both of them are small, 10 tanks and 10 tanks. So both of these samples are less than 30. If either one was, we would have to go to a t-stat. I believe the last time I ran a p-value test, so this time let's go with the rejection region. My rejection region is right here. I need that line in the sand. That line in the sand is when I have the alpha amount entirely over here, 0.45 left in there. So this alpha, 0.05, is in the rejection. What is this t-score right here? Well, my degrees of freedom, I'm giving it to you here to be N1 plus N2 minus 2 here. That's because in this cases, we have almost equal variances. Notice, for example, I got 0.8 and 0.82 for the standard deviations. Approximately equal means the larger one will not be more than 50% greater than the smaller one. If this is the smaller one, the larger one would have been more than 1.2, that would be 50% greater. Then I would have said unequal variances. But these are relatively equal. I'm using this degrees of freedom. So that's going to be 10 sample size plus another 10 sample size minus 2. 10 plus 10 minus 2 is 18 in this case. So I have 18 degrees of freedom at 5%. I go to my t-chart, 18 degrees of freedom. Column of 5% gives me 1.734. 1.734. That's a negative because it's on the left, 734, excuse me. 1.734. It's on the left side, so it's negative. If my t-score goes over that, if my t-score, my rejection region would be, t would be less than that line in the sand, negative 1.734. These must both be on the left side to be consistent. A common mistake right here, people would have put t greater than a positive 1.734. T greater than a positive would have been over here. Didn't really matter. I needed to see if it was on this side. It's because of how we set up the difference. On these small samples, either I'll give you the t-score or I'll give it to you in a printout. All you have to do is recopy it down. So your t-score turns out to be negative 4.14. It's way over here someplace. Way over our line in the sand. Consequently, our step number 4, t equal to a negative 4.14 is sufficient evidence to reject our null and now conclude, and I need to put this conclusion in context of the problem. What were we testing? The miles per gallon of the Edge versus the Explorer. Conclude the mean miles per gallon of the Edge is greater than the mean miles per gallon of the Explorer. Again, sufficient evidence, we make a conclusion. If it had been insufficient evidence, we would have continued to assume the null, that there was no difference. That concludes that problem. I don't have to run a confidence interval for this one. Let's take another example. Here's one where I'm giving you a computer printout. Go ahead and read the problem once, and we'll just finish it off. Well, I don't want to start some controversy that some particular sex talks on the phone more than another, whether it's male or female, but this was a study that was ran. We're going to run a p-value hypothesis test. Okay? First thing I got to do, again, is define what each population is. I take the first one given from U1. The first one given was for women, so this would be the mean time for women. This would be the mean time for men. Now I go over and I list my null. And my alternative. Both of them are going to be describing a difference. It doesn't say is one 3 minutes more than the other, it just says, is there a difference? Let me double check that once. Okay, it says, was there any difference up here? That is screaming at me a two-tailed test. Remember, a two-tailed, the null is always equal, the alternative is unequal. Visually, what that means, no difference would be that one. There's some part over here that the difference would be negative, or some part over here where the difference would be positive. If these differences are either so negative that it goes that far over, or if they're so positive that they go that far over, negative would be where the second one is greater, positive would be where the first one is greater. If I go far enough away from zero in either direction, I know that there is, in fact, a difference, or there's evidence that's statistically significant to indicate a difference. Okay? Step number 2. I need to list the sample sizes. I had 28 and 28. I first have to list my alpha, excuse me. Okay? They don't list one here. They do right here, significance level of 0.05. My sample sizes were both the same, both at 28. Because at least one of them is less than 30, I'm going to use a t-stat. They wanted me to run a p-value test here, so I don't need a rejection region. I don't need to calculate the t. They give it to me. Critical value, test statistic, right here it is. Test statistic, in this case t, is 1.89566. They give me the p-value directly. Notice they tell it is 0.06317. I just need to copy it in the correct location. Remember, this whole thing here is a procedure, an argument, a type of proof, if you will, for what we're trying to show. We check our p-value. Is it less than alpha? If it is, then I have sufficient evidence to reject the null, conclude the alternative. If it's not, which it's not in this case, it's not less than 0.05, 0.06 is not less than 0.05, then I have insufficient evidence to reject the null. I got to continue to assume they're the same. I need to conclude that statement. So P equal to 0.06317 is insufficient evidence to reject our null, and thus we continue to assume, now the context, I continue to assume there is no difference between the mean length of call for women versus men. There wasn't enough evidence to indicate that there is a difference. In this case, there wasn't enough evidence that we were that far away from the zero. Our t-stat was about a positive 1.8, which is about over in here someplace. It's within reasonable variance. It did not go over our line, That's why we had insufficient evidence. We have to continue to assume the difference is zero, which means there's no difference. Okay? They also wanted us to look at, interpret the 95% confidence interval. Well, that's given in your computer printout. Because it goes from a negative to a positive, the difference could have been negative. The difference could have been positive. We're not sure if it's less than zero or greater than zero, which is why we had to continue to assume there is no difference or the difference equals zero. Had this been entirely negative, we would have had evidence to indicate a difference. Had it been entirely positive, we would have had evidence to indicate a difference. But it matches up with our conclusion that we had with our hypothesis test. Got one more example here. Be our last one of this particular lecture. I'll let you go ahead and read that for a moment. I hope you appreciate what the problem is about. What the problem is really studying, testing, if you will, is do hospitals let people stay in their hospital longer if they have insurance? Or if they don't have insurance, do they send the people home sooner to try and save them some money? That's a question many, if not all, insurance companies are always checking. They're checking it because if they can show that there's evidence that they're in the hospital longer when they have insurance, it would be the hospital trying to bleed an insurance company out of that. Now, the insurance company might be thinking, well, we're just trying to save some money for those that are uninsured. But from an insurance company's perspective, that is not equal. That's not fair. So they're running this kind of test frequently. Okay? The first thing I got to do is define what my variables are. Both of them are going to be the mean of something. The first one given is for the insured people. So the mean time for insured. This would be the mean time then for the uninsured. Now I'm ready to go to my null and alternative hypothesis. Again, because I have two populations, both of them are describing a difference. Let's see if it's two-tailed or single-tailed. Is there strong evidence to indicate the mean hospital stay for routine childbirth for uninsured patients is less than? Okay, this would be the uninsured. That's the second one. We're testing if that one is less than. If the second one is less than, it's the smaller number, bigger number minus smaller number, that would indicate a positive difference greater than 0. This one would likely be tested against just 0 itself. You could have put less than or equal to, but this one had to be greater than. This is the one I'll be looking for at the test time. Again, you got to define what they are, because without these two definitions, this has no meaning. You have no idea which way you're subtracting. So this must be in there. Okay? Step number 2, our alpha level. Strong evidence indicates alpha is 0.05. Our sample sizes in this particular case, 2 samples of 16 were used. So each sample was 16. Both of them are less than 30. If either one of them is, we're going to be using the t-stat. We're using a p-test this time, so I do not need a rejection region. I've given you the t. We just simply have to copy it down. They give us the p-value. They tell us it's between 0.01 and 0.02. I don't know exactly where it is, but it doesn't matter because any place between those two is less than my alpha, which means I got sufficient evidence. So I'm going to write that down now. P less than 0.02, could have put greater than 0.01, but this was the key part. It means that it's going to be less than 5, is sufficient evidence to reject our null And now conclude. What am I concluding in context? I'm concluding the mean length of stay for a routine, how do they word that? Routine childbirth I am concluding the alternative. So I'm concluding in this case that the mean one for the insured people is greater. Mean length of the stay for routine childbirth of uninsured is less than the insured. I could have put the routine childbirth of insured is greater than the uninsured. Write it either way, as long as it's clearly written. Okay? That is my concluding statement. They didn't ask for a confidence interval. On all of these, I want to emphasize again, I'm either going to give you a computer printout, something like this, or I'll give you the t-value and a degrees of freedom or a p-value that you can figure it out. But this is writing it all out. This is what we're looking for our hypothesis test, okay? On your test, I'll be expecting that you write this all out again. Again, don't take any shortcuts in the conclusion. Make sure that it's written out really clear in context. Number all your steps. If you leave the numbers off, you get deducted. If you leave some part out of this off, you would get deducted. Those all have to be in there. So again, just take special note what that is. Okay? Finally, I'd like to clarify now your assignment for 10-1. So watch carefully what I have here for this assignment. I'm changing this assignment from the syllabus slightly, making it a little bit shorter. One of the things that I was disappointed in the possible problems that I could assign for you is none of them gave problems where both samples were 30 or more. To that end, I have posted on Blackboard an assignment for 10-1. It's going to give you one problem where both samples are large, which means, of course, you're using the z-statistics. It would be something similar to what you had in the lecture 10.1 part 1. Then in the book problems, the ones that are from your assignment, from your syllabus, we're going to omit number 4 and we're going to omit number 8, both of those. For number 11A, that's part of your assignment in your syllabus, I want you to only run the test for alpha to be 0.05. In part B, they give you a whole bunch of alpha levels. Just run the alpha at 0.05 only. And this, make sure that you get this. There's a printout. They call it figure 10.6. It's on the next page, page 397, to get all the details you will need for this test. So when you're doing number 11A, look to the next page for figure 10.6. It's a computer printout that gives you the details you'll need to write this test out. But you will run the test, run the entire test out, write it all out at an alpha equal to 0.05. Likewise, for number 12A, that one is also in your syllabus. Similar to this one, I want you to run the test at alpha to be 0.05 only. You don't have to use multiple alpha levels. This one also has a printout. It's figured 10.7. The last one was 10.6. This is figured 10.7. It's on the next page, page 397, to get your details as well. So basically, make sure that we catch all of this. Our entire assignment is just 3 hypothesis tests. We're first going to do the one printed in Blackboard, listed as under content. Then we're going to do 2 from our book. Both of these 2 from our book are small samples. Both of them have computer printouts, 10.6 and 10.7. All of this is for your assignment, 10.1. Okay, hopefully that is clear enough, and we will see you next time.